Steel shaft in bending has an ultimate strength of 690 MPa and a shoulder with fillet of 3 mm connecting a 32 mm diameter with a 38 mm diameter. So what's going on here is basically like this. This is 38. This is 32. So there's a 3 and 3 mm fillet at both edges. Okay, so we need to estimate KF. Okay, and I'll show you that you can get the same answers if you use the figure, that is that plot of Q versus R, as well as using the equations which involve the Newberg constant. So we'll do it both ways and you'll see that the answers match. So let's do it. So let's go to A. Okay, so I'm just going to, it's just basically going off from this. So just 3 steps. Okay, we're going to follow this 3 steps and get a value for KF. So we need, in this case, this is bending. So we are not computing KTS or QS, we're just computing KT and Q. So let's get KT first, then Q, which by the way comes either from the figure or it will come from those equations. And then KF is very simple, it just depends on Q and KF. Yes, so it's one step at a time. So first, compute KT. So KT is the stress concentration factor. It has nothing to do with fatigue loading. It's just to do with bending when there is a change in geometry. So what we need to do is we need to go look at the appendix and see the KT for this particular geometry subjected to bending. Okay, so what I did was I pulled that up in advance. So let me just insert that. So this is the appendix. Cheers. So it's A15, 8:15:9. Okay, so we see that KT depends on the ratio of R divided by D, where R is the fillet radius, D is the diameter of the smaller shaft. So R in this case is given as 3 mm, so 3, and the diameter of the smaller shaft is 32. So R divided by D is 3 divided by 32. That is 0.09375. Okay, so 0. So it's very close to 1.1. But there's another factor, which is capital D divided by D. So we need to compute that too. So capital D is the diameter of the bigger shaft, which is 38. And the smaller shaft is 32. So D divided by D is 1.1875. Okay, so how do we do this? Well, we can either start from this 0.1 and then see where's 1.1875. This is 1.1. I guess this is a good estimate. So 1.6 is just above that. So I don't know, 1.5 or 5.5. Just take 1.5. Okay, so there's some wiggle room there. You could choose 1.5. Really, anything between 1.5, 1.67 should be fine, because that line can actually be above. So let's choose KT. .5. Okay, step 2. So going back to this algorithm, step 2 is compute Q, which comes from this figure. So we are looking for bending and axial loading. So we need the notch radius. The notch radius in this case is the radius of that fillet. So the radius is 3 mm. It's an inch. So we need to convert 3 mm. Is it 3 mm or 3 inches? I think 3 mm.
Can we look at the bottom graph?
3 mm. So I'm going to convert 3 mm to inches. So 3 mm is 0.19 inch. Oh, it's off the chart. So it's off the chart. And we also need SUT. And I think our SUT is given as 690. Okay. So 690, we need 690 and that measurement. 690. Oh, it's given in. So we have KPSI. So we need, my bad. Here it's given in GPA. I'm surprised they have also given it in mm. My bad, I should have seen this. So 3 mm. Okay, my conversion was off for some reason. This is 3 mm. 0.2. Yeah, good. Yeah, somebody got it that it should top. So 3 mm is here. And we also have 690 MPa. So 690 MPa is also 0.69 GPa, which is about 0.7. So 0.7 is right here. And so it's just this point. So it's this kind of convenient. This is fairly straightforward. So it's somewhere between, I think this is 0.9. No, somewhere between 0.8 and 0.9 looks like. So let's just assume it's 0.85. 0.85 for Q1. Step 2, we have KT is 0.85. Sorry, Q is point. Use R equals 3 mm. And SUT is 0.7 GPa. Okay, in step 3, compute KF and KFS by using this formula. So 1 plus Q, KT minus 1. So KFS is 1 plus Q, KT minus 1. This should be KF. 1 plus Q is 0.85. KT is 1.5 minus 1. So that is 1.425. Okay, we've done this calculation using the plot, the figure. Let's see if we can do it with these equations 3 and 4. So let's see what equations 3 and 4 are. They are right here. 3 is this, and 4 is here. So this is going to give us KF directly from KT. So we need KT, and we need the value for square root of A and R. Okay, so I'm just going to write this formula, and then we just go from there. So number 2, use KF equals 1 plus kt minus 1 square root a divided by square root r. Okay, so r is 3 mm. You know that. Kt we already computed, it's 1.5. It's the same process. Go to the stress concentration table. And then the last one is square root a. So let's see what the formula is for square root of a. So we are looking at bending and we have kpsi. So we need to use the formula for a. I'm just going to plug this. Oh, my bad. Sorry, my bad. It's in MPa, right? SUT, it's 690 MPa. So we should use the second one. Okay, so 1.24 minus 2.25. SUT is 690. 1.6. 690 square minus 1.11. 690 cube. And so if you compute this, the answer is in mm raised to half, comes out to be 0.314 mm raised to half. And so we are all set to use this formula for kf. We know kt, we know r, and we know square root of a. So kf equals 1 plus 1.5 minus 1, 1 plus square root of a, 314 square root of 3. Okay, I get 1.42. 1.423. Yes, which is 1.42. Okay, so let's read it. So this is the figure 622A. Shows a rotating shaft simply supported. There are two reactions in ball bearings at A and D, loaded by a non-rotating force F of 6.8 kilonewtons, using ASTM minimum strength estimate the life of the part. So, but when it says ASTM minimum strength, it basically gives you the SUT, which I put down there. So you don't really have to go to the ASTM minimum strength and figure out what the strength, the ultimate strength is. So this information is, this is all you need from that standards. Okay, now I have here simplified this problem in so many ways by giving you what is the critical point. Say the point is B. Okay. Right, so let's come to that. So if that's not given, let's say that you don't know what the critical point is. And remember, you want to design based on the worst case scenario. That is, figure out where the stress is the maximum, and that's your critical point, and that will lead to failure. Now, if that's not given, then in this case, since this is loaded by loads which lead to bending, we are interested in not the shear stress, but in bending stresses, normal stresses, sigma. So sigma comes from M. So they have provided a bending moment diagram. Okay, they have not put the values there for the bending moments at different points. But what you notice is that there is the maximum bending moment is right here, where the 6.8 kilonewton force is applied. At MB, there's another moment, and MC, there's another moment, right? Now, clearly, if there was no stress concentration, it was uniform geometry, then M max, would be the point of maximum stress. And so you design based on that. Now, what happens though is that because B and C have a change in geometry, there's going to be stress concentration. So the stress at B and C will be multiplied by KT. So E, KT, sigma C. And the stress at, let's call this point E. The stress at E is going to be just sigma E. So these are the three stresses. Okay, for a second, just assume that there's no static loading, there's just static loading. Yeah. Right. Right. That's right. So what we need to do is to figure out the point of the critical point is we need to compute these stresses, sigma 1, sigma 2, and sigma 3. And whichever has the biggest magnitude of the stress is going to be the point of higher stress, and that's going to be the critical point. Now, in this case, I've already given to you that the critical point is P. This is already given, but otherwise you would have to compute that by computing those stresses. So it's going to obviously take us a lot more time to do that. So I'm just skip that step, but that's what you would do. In fact, you would just compute the stress along the entire shaft in a real problem and then figure out what the maximum stress is. Yeah, question? So it's given in the table. That table I skipped. It's not very important. So it's just like this. Yeah, it's given. So that information is the. Yeah. Yeah, there will be. So in this case, you will be able to do this with finite element. Yeah. The only issue is that there are issues at whenever the stress concentration finite element it has problems because the stresses grow very quickly, and then the question is how small a finite element do you need in order to capture that stress? So there are problems there, but nevertheless, yeah, you will do it. For example, you design it first round, you just use a software to do it, and then perhaps make a prototype and load it and see where it fails, and then use that to do your next iteration. But yeah, that's how I'll do it. Okay, so let's see where we got lost. Okay, so we have to compute the life of the part. Okay, what is the life of the part? It is basically N. That is unknown. Okay, so far we know that the life of the part is, and this is for fatigue loading, right? So we know for fatigue loading, the life of the part is A n raised to B, where there's a formula for A, there's a formula for B. Let me just pull those up. The formula for A is F SUT squared divided by C. B is a third log to the base 10. CF SUT. Okay, so let's sort of think of it backwards. We are asked to compute N. We need A and B. So A comes from F. F comes from a table. SUT is given. The endurance limit is, well, that is also from a formula which is readily available. So all these things are known. So A is known and B is known. Okay. So then the question is, do we know SF? So the way you can compute SF is that SF is the stress at B, because B is the critical point. Now, how do we get the stress at B? Well, we get stress of B if we can compute. So it's based on M at B. Clearly, we want to compute MB, which we can compute from a bending moment diagram. But then there's a change in geometry. So we need a KT, but we can't use KT here because this is not static loading. It's variable loading. So we need to compute KF. Okay, so the stress in this case would be KF times the stress at B. This will be due to MB. So that's like the entire solution of this problem. And we just need to work out the details now. So what we'll do is, just to make it easy, we'll do this part first. Okay, and then we'll follow up with this part. And then once we compute SF, we will know SF, we can compute N. So that will be part 3. Okay, so let's just work through this. So most of it is just tables. So let's get started. So part 1. I'm just going to pull the formulas for these things. So we remember we need SE. What else? We need SEF, and we know SUT. So SUT is given 690 MPa. SE is Ka, Kb, Kc, Kd, Ke, Se prime. For Se prime, for Se prime, there is a empirical formula. It is 0.5 SUT if SUT is less than 1400 MPa, which by the way is, yeah, it's 14, that's good enough. So 1400 is less than 690. So 1400 is greater than 690, so that's true. So this is 0.5 times 690. So that comes out to be 345 MPa. Okay, so now we need to dig in through those tables to compute Ka, so on to Ke. Ka. Okay, so Ka, remember, is the constant which depends on the type of finishing. Right? In this case, the finishing is machined from, and so I can see these keywords, machined from cold drawn steel. So let's see if there's something for that. So machined or cold drawn right here. So there are two values for A, one depending on KPSI MPa. We are in MPa, so 3.04 and minus 0.217 for B. So I got it right. 2.0 and 3.04 and minus 0.217. Okay, so I have that available. It's 0.714. Okay, KB. Okay, KB. I'm banking on what KB depends on. Just put here. It's a size factor. So there are two cases. There's one for rotating and there's one for non-rotating. And I remember this was non-rotating. So for non-rotating, there's a table. It's in the next page. Yeah, so this is a non-rotating specimen. So we need to use the adjusted diameter DE, which is 0.370 D. So what do we do with DE? Well, once we have DE, we need to use DE in these equations to compute KB. Okay, so we're looking at, this is in SI units. Yeah, everything is in SI. So let's just pick the one for SI. Let me pick this up. Okay, this is just for a reference. You don't have to copy this. This just came from somewhere else. Okay, so let's compute DE. That's 0.370 D. Okay, so D is the diameter. So let's go back to the figure and see what the diameter is. 32 and 38. So the critical one is the smaller one. So let's use 32. So 0.370 times 32, smaller dia is critical. So that is DE. Yeah. Yes, so it's non-rotating, right? So let's see. So first of all, oh, my bad. What should I read? For some reason, my bad. The force is non-rotating, but yes, this is what is important. Good catch. This is, yeah, my bad. So you don't need D, but I already showed you how to do D in case it's non-rotating. So the shaft is rotating. It's not a non-rotating shaft. So I don't need to, what's that? I don't need this. This is not needed. The shaft rotates. Okay, so then D is 0.330. Remember the D is in mm, and I presume that the dimensions are in mm. So we just go KB equals 1.24, 32. That comes out to be 0.86. Okay, two factors knocked down. So in case this was a non-rotating specimen, what you would do is you would take this DE and then use this D in this equation. Okay, that's the thing. So you'll see that the diameter reduces because it's non-rotating.
The rotation of a shaft doesn't matter, right? The
Yeah,
force doesn't matter.
force doesn't matter, right? Okay, so got KB. Let's see what KC, KD, and KE is. K. The load factor, bending axial torsion. So KC is 1, so I wouldn't even bother. This is a temperature effect. I don't think there's anything mentioned about temperature. We'll assume room temperature, so we don't have to adjust for KD. And then the reliability is not given, so we assume that that doesn't affect. So we just ignore that. So K, C, KD, and KE are all 1. KD is 1 because there's no temperature effect. So assume that room temperature. Okay, so we've computed all these factors. We also got SE prime 345. So let's compute SE, which is this formula. So SE is Ka, which is 0.74, Kb, which is 0.86, Kc, which is 1, Kd, which is 1, Ke, which is also 1, and then 345. So it comes out to be 220 MPa. Okay, next is we need to compute F in order to get the factors A and B for fatigue loading. So for F, there are two ways to compute F. One is you can look at a graph of F versus, I believe, SUT, and the other one is there's a formula for F. So let's just recap that. Let's go a few lectures back to lecture 23, I think. Yeah, there it is. F as a function of SUT. So we know that SUT is, this is given in kpsi. We given it in 690 MPa. So I don't think the book provides a table. So you need to either convert from MPa to kpsi, or we'll use the other method, which is there's also a formula, and this formula is available for both MPa as well as for kPa. So let's just use this. Okay, so that's from lecture 23. Okay, you don't have to copy that. It's just that for reference, but I'm going to use the formula here now next. 1.06 minus 4.1, 10 raised to negative 3, SUT is 690, plus 1.5, 10 raised to negative 7, 690 square. So plugging in those values, you get 0.85. Okay, so now we are all set to compute the factors A and B for estimating the life. So A is FSUT squared divided by SE, which is 0.85 times 690, the whole square, divided by 220. The answer is in MPa 1564 MPa, and then B is a third log to the base 10 SE divided by FSUT, which is 1/3 log to the base 10. SE is 220.85 times 690. So B is minus 0.142. Okay, so just recollect why we are doing all this. We need to compute the life of the specimen, which is N. We've so far computed A and B, which are these values. And SF is unknown. Right? So we are trying now, let's go to the second part, which is computing SF. And that comes purely from, one is the bending moment diagram, and secondly, it comes from the KF factor. Okay, so let's compute SF next. This is part 2. Okay, for that, I need to take a look at the figure and redraw this figure in order to compute MB. So I probably need, so there's only one load, 6.8 kilonewton. And the distance, this is what I would need, is 250 plus 75, which is 325. And then this distance is 100 plus 125, so 225. So I would need to draw a free body diagram in order to figure out MB. So my goal is to compute MB now. Let's do that. So this is part 2, free body diagram. The beam acted by R1, R2. The load, which is slightly skewed to the right, which is 6.8 kilonewtons. These distances are 325 mm, just 325 and 225. Okay, now let me just skip computing R1, R2, but you know how to do it. It's just summation of forces in the y direction and taking the moments about any point and equating them to 0. So I'll not do that, I'll skip that, but I'll give you the values for R1 and R2 using summation of forces at some point equals 0 and summation of forces in the y direction is 0, gives me R1 equals 2.78 kilonewtons and R2 equals 4.02 kilonewtons. Okay, so let's just straight away go and figure out the bending moment at, again, to remind you, we need to compute the bending moment at B, so point B, so which is at 250 mm to the left. So we just draw a free body diagram by cut the beam at B and then draw a free body diagram and compute moment at B. We're not interested in doing anything else. So let's just do what we need to do. So this is the beam. Reaction force of 2.78 kilonewtons. This distance is 250. Then we want to compute the moment at B. This is B. So it's clear that MB is, so I probably need to convert the units. This is 250 mm. So MB is going to be 2.78 times 10 raised to 3. This is converting kilonewtons to newtons. And then this I need to multiply with -3 to convert millimeters to meters. And so M at B is 695 Newton meter. Okay, that's just the moment. We need to compute now the stress at B. Okay, the stress is related to the moment using the equation M B y divided by I. Okay, the normal stress, the stress sigma B is going to be the maximum at the outer edge, right? It's going to be 0 at the neutral axis. So to compute that, we need to find the point of maximum stress. That would be when y is maximum and y is measured from the neutral axis. So if you look at this, should be at the radius. But if you look over here, of the 2 points, so we're looking over here, we can choose either radius to be or diameter to be 32 or 38. We go with 32 because it has an inverse diameter relation. So the smaller the diameter, the bigger is the stress. So we'll use the smaller diameter. So what I'll do here is I'll first put in the value for y, which is the radius, which is d divided by 2. And then this is pi d raised to 4 divided by 64. That comes out to be 32 m divided by pi. I guess it's now obvious that which of the diameters is more critical. If you put, you can see that the diameter appears in the denominator. So the smaller the diameter, the bigger is the normal stress, sigma b. So between 32 and 38, I would use 32. Gives larger sigma b 32 by pi 695, and the diameter is 32 times 10 raised to negative 3, and I need to take the cube of that. Okay, so this will give me sigma b equals 216. Okay, we're not done yet. We need to ultimately compute the stress at V due to fatigue loading. So if there was no stress concentration, then this would be the stress you'd use in the equation. But since there is a change in geometry, we need to compute Kf. So next is to compute Kf. So the stress SF will be Kf times sigma b. So sigma b is, we've computed that. We need to get Kf based on this geometry. So if you look at this figure, this is 32 mm, this is 38 mm, and there's a change in diameter. So we're looking at something like this. 32, 38, and this is subjected to bending. Okay, now to do that, what we need to do is step 1 is compute KT for this geometry. Step 2 will be compute Q, and step C would be compute Kf as 1 plus Q KT minus 1. So luckily we have done this calculation in the first problem. We take the similar geometry and computed it. We have already computed Kf for this geometry in Q1. Let's save us some time. I just have to read it off. So Kf was right here. Kf, I got 1.425 using one method, and then I got 1.423. Let's just use 1.425. Okay, so we've got that, and so now we can compute SF is 1.425 times sigma b, which is 216. So that comes out to be 0.425 times 216. 307.8. 308. Okay. So step 3 is the final step. SF is A n raised to B. N is SF divided by A is 1 divided by B. And so I'm just going to get SF from here, 308 from top, and then A was computed in end of part 1, so that's going to be what was 1564. And B was also computed, was minus 0.1419. So it comes out to be about 94,000 cycles.